In this video today, we're going to be going through the 2B2 notes. We're going to be talking about symmetry. And you guys have studied symmetry in the past, but we're going to study it a little bit more in depth today. Before we get started, what I want you to do is pause the video as you reflect segment AB in the line y equals negative 1/3 x, where A is 1, 3 and B is 3, negative 1. Do this one on your own, and then we're going to use this in order to talk about line symmetry. Alright, now that you've done it, if you are getting stuck, let's talk through this together. I graphed A and B. I graphed the line of reflection. Remember, that's a dashed line. And now I need to reflect A and B in this line. Well, if I look at A, I know that the line containing A prime, must be perpendicular to this line y equals negative 1/3 x. The slope of negative 1/3 x is negative 1/3. That means the slope of the line perpendicular, or the slope of A prime, must be equal to the opposite reciprocal, or a positive 3, or positive 3 over 1. So to graph this, lightly, I'm going to go to A, and I'm going to have a line of, that's the slope of 3 over 1. So rise 3, 1, 1. I can go in the opposite direction. And I'm going to lightly graph this just to help me with figuring out where A prime is. Now, I know not only is this line containing A and A prime perpendicular to the line of reflection, I know that A is also the same distance to the line of reflection as A prime is. So I have to go down 3, right 1. I'll have to go down 3, right 1 again. And this right here is where A prime will be. I'll go ahead and do that in red to show its image. So this point right here would be A prime. Make sure we use prime notation to label that. And now we're on to B. Well, the line containing B and B prime also has to be perpendicular to the line of reflection. But when I look at this, in order for B to be the same distance from the line of reflection as B prime is, it has to be right on the line of reflection. Because B is right on the line of reflection, B prime will also be. So we can put B prime right here and then connect these 2 points to draw the segment AB. Or sorry, A prime, B prime. So that is what the transformation would look like. When we look at this, I want to use this now to talk about line symmetry. So I want to talk about the definition of line symmetry. Scooching down here. I think we can zoom in a little bit too. Oh, let's focus, focus, focus. There we go. Okay. A figure in the plane has line symmetry if the figure can be mapped onto itself by reflecting in a line. This line that we are reflecting in, we call that the line of reflection. That's what I highlighted in blue. So we'll switch over here. Line of reflection. Maybe we do need to zoom out to see everything. Sorry about that, guys. Let me show you this with tracing paper as well. What it means is if I can take this figure and I can flip it over the line of reflection and map it onto itself, then this figure has line symmetry. Meaning the figure we're talking about would be this kind of V shape right here. This V shape has line symmetry because I can map it onto itself by reflecting it in a line, and that line is called the line of reflection. This V shape has one line of symmetry. Line of symmetry. We're going to be talking about some that have multiple lines of symmetry as well. Scooching down here to talk about rotational symmetry, I want you guys to perform this rotation. Quadrilateral ABCD has coordinates given here. I want you to rotate this quadrilateral about point D. So your center of rotation is this point right here. I'm going to highlight in blue. That's our center of rotation. Excuse me. I want you to rotate it 90 degrees, 180 degrees, and 270. And remember, it doesn't tell you which direction, so think through what that means. Go ahead and pause the video and do this transformation right now. Now that you've tried this on your own, let's go ahead and do this together. First, if I rotate 90 degrees, well, 90 degrees, and it doesn't say which direction, means that we will be going counterclockwise, so we're going that direction. So I'm going to start at D, and let's first start with point A. Now, to go from A to D, this is a slope of -1/2. So the slope of AD is -1/2. To rotate 90 degrees means that I'm going to have a right angle, which means that AD will be perpendicular to A prime D. Therefore, the slope of A prime D must be equal to the opposite reciprocal, or a +2, or 2/1. So when we go here, D, a slope of 2/1, we rise 2, run 1, or we can go down 2, left 1. And we got to decide which direction, which one of these is really A prime. Well, to go from here, we're rotating counterclockwise 90 degrees. I know that this one right here will be a rotation 90 degrees. So this guy right here is my A prime. Okay? Now I'll do the same thing for B. The slope of BD is equal to, well, I rise 1, run 3, 1/3. I know that BD will have to be perpendicular to B prime D if what's going to be a 90-degree turn or a right angle will have to be perpendicular, which means that the slope of B prime D will have to be equal to a -3. So here, again, I'll go from D. A slope of -3 means go down 3, right 1, or up 3, left 1. It's one of these 2 points. Let's erase this other one. We knew that wasn't A prime. So it's one of these 2 points. Now to rotate 90 degrees means I started here. I rotate 90 degrees counterclockwise, so that will be this guy up here. So this point is the point B prime. I'll erase this point here. And I'll do the same thing with C. The slope of CD is equal to rise 1, 2, 3, 4, run 2, 4/2. I know that can be simplified, but I'm not going to simplify that because by keeping the 4 and the 2, we'll make sure that the distance, the length of CD remains the same. So I know that CD has to be perpendicular to C prime D, which means that the slope of C prime D would have to be equal to a -2/4, which I know, again, simplifies to -1/2, but I'm not going to simplify it to make sure that that length is preserved. So I go from D, and now the slope could be a -2, run 4, either here, or rise 2 to the left 4 here. Now to go rotate counterclockwise 90 degrees, that means I'm going this direction. So this point right here is C prime. And D, because D is the point of rotation, will remain here. So D prime is going to be right where D is. I'm not going to bother drawing that in. But we can draw in the segments here so we can see the quadrilateral. There we go. So we got the first piece. That was the 90 degrees counterclockwise. Now we have to do 180 degrees. Well, if I rotate 180 degrees, that means that the segment AD and the segment A prime D will be on the same line because 180 degrees is a straight angle. So here, do this in a different color. Let's see if this green works. If this is up 1 to the left 2, I can go up 1 to the left 2 again, and there's your A double prime. For B, I go down 1, left 3, down 1, left 3 again. There is B double prime. And for C, go down 4, left 2. If I go down 4, left 2, that will make a straight angle, or 180 degrees. C double prime. My pen's running out. So that's our C double prime. So if I draw in this quadrilateral now, I have this guy here. And the last one, 270 degrees. I know that's really like 90 degrees in the opposite direction, so 90 degrees clockwise. So I'm going to use the same analysis. Again, if AD has a slope of -1/2, now we're not talking about A prime, we'll talk about A triple prime, we'll have to have a slope of 2. So I rise 2, run 1. That would be if I went clockwise, counterclockwise, but if I went down to left 1, this would be if I went clockwise. So that'd be clockwise 90 degrees or counterclockwise 270 degrees. Ah, my pencil keeps breaking. So this is a triple prime. Same thing here. With B, BD has a slope of 1/3. So B prime D will have a slope of -3. So I go down 3, right 1. Or I could go up 3, left 1. Up 3 to the left 1 was if it was 90 degrees counterclockwise. To go 90 degrees clockwise or 270 degrees counterclockwise, this is where B triple prime would have to go. And I do the same thing with C. I went up 4, right 2. So I'd have to go, the opposite reciprocal would be down 2 to the right 4, either over here or up to the left 4. Well, that's where 90 degrees counterclockwise is. 90 degrees clockwise would be right here. So there's C triple prime. And here is, we draw this in. Now we have this. So what I want to do to talk about rotational symmetry then is to look at this object. It kind of looks like a pinwheel. I'm going to highlight it in orange. So this polygon has rotational symmetry. I want to talk about what rotational symmetry is. So rotational symmetry can be defined in the following way. A figure in a plane has rotational symmetry if the figure can be mapped onto itself. So far, the same definition as we had before, so mapped onto itself. This time, instead of by a reflection, we're going to say by a rotation. Now we got to specify this rotation though. It has to be a rotation greater than 0 degrees and at most 180 degrees about the center of rotation. When we talk about the center of rotation, that's just the point that we're rotating about. I highlighted that in blue here, so I'm going to box it in blue here. There you go. So the degrees of rotation, that answers the question, how many degrees must you rotate the object in order to map it onto itself? Now remember, you can only rotate it, it has to be greater than 0 degrees and at most 180 degrees. So when we talk about this, if x is the degrees of rotation, it has to be less than or equal to 180 degrees, but greater than 0 degrees. So for example 2 that we just did, go ahead and try and figure out what would the degrees of rotation be for example 2. Now that you've tried this on your own, let's talk through it. If I take this pinwheel here, okay, this is our center of rotation. We had this pinwheel. Okay, there we go. I've traced it. I'm going to put a little asterisk here so we know where it started. So we start up in that corner. I have to figure out how many degrees do I have to rotate about the center of rotation to map it onto itself again. So I turn, and now it's back onto itself. So there's your 90 degrees. If I turn, that's 90 more degrees or 180 degrees. I could do it again and get to 270 degrees, but we don't talk about that because that's just like going 90 degrees in the other direction. So this pinwheel has 2 different degrees of rotation, 90 degrees and 180 degrees. So that summarizes rotational symmetry for us. If we flip to the back, I want you to place all of the capital letters in the alphabet in the Venn diagram. And now when we see the alphabet, I want to specify, this is the English alphabet, so like what you see written here. So I know there's a lot of alphabets. We're talking about this English alphabet. So what I want you to do is create a Venn diagram. So place the letter A somewhere in here. Place the letter B, all of the letters in the alphabet. When you are in this little sliver here, this means you just have line symmetry. This means you just have rotational symmetry. When you're in the middle, you have both line symmetry and rotational symmetry. When you are on the outside here, it means that you have neither line symmetry nor rotational symmetry. So that's what that box on the outside means. That might be new to you. You might just be used to seeing the 2 circles. But outside means you are neither one of those things. Go ahead and try this one on your own, and then we'll talk through what I got for my answers. So pause the video, try it on your own. Now that you've tried it on your own, here are my answers that I got. I circled some of these because there's some room for debate, okay? So things like A, C, and D, I would say they all have lines, they all have line symmetry, meaning I could kind of cut it line here, line here. This one has a vertical line of symmetry, vertical line symmetry, and so on. Some have vertical, some have horizontal. There's some that are debatable, and I circled those, so we'll talk about those in a second. If you look at rotational symmetry, N, here's your center rotation. I can rotate it and get it back. Z is the same way. S is the same way. These guys in the middle have both rotational and line symmetry. So I can cut H like this, or I can rotate it and have it upside down, and it'll map it back onto itself. Same thing with I. And X and O can rotate. Now, rotate and have line symmetry. The ones on the outside have neither. So for F, G, J, R, those are ones that you cannot draw a line and map it onto itself, or rotate it and map it onto itself. If we look at B, some people would argue that the 2 little humps when we draw a B are different sizes. If you write them different sizes, then it would be no symmetry. But if you make them the same size, then it would have line symmetry. For E, again, if these 2 are different sizes, you would say, well, there's no symmetry, but if all 3 of these are the same, or maybe the top and bottom are at least the same, then this would have line symmetry. With K, same idea. If the top is the same as the bottom piece here, these would have line symmetry, but if the top is smaller and you got kind of like a bigger bottom, then that would not be line symmetry. With Y, if you make a slanted line here, this would have neither, but if you have a vertical line, then this would be line symmetry. And with Q, if you have this so that it kind of cuts right down the middle, this could have line symmetry that's kind of on diagonal. But if you say that doesn't like go right down the middle, then I could see where you would argue that it's neither. And then finally with S, it would have rotational symmetry if these S's were the same size on top and bottom. But if it's like a small top and a big bottom, then it would have neither. So those are just the different answers, good ones to think through. What I want us to do now is look at examples 4 and 5. For example 4, I want you to, for the letters B, X, and O, I want you to draw all the lines of symmetry. For the letter B, because we said it's going to have line symmetry, I want the humps to be the same. So imagine that those are the same. I know I don't do a great job of drawing it. For X, imagine that these are perpendicular. So it's not like an X like that's this, like skinny. It's like just these are perpendicular segments making the X. And for the O, we're going to assume that that is a circle. We're going to go ahead and assume that that is a circle. Okay? And then, so go ahead and pause the video and draw in all the lines of symmetry right now for me. And then we'll discuss it. All right, back up here when you look at for B, now that you've tried this on your own, I say this would only have one line of symmetry. Going like this, I'm going to draw it with a dashed line. So that's just one. For X, say that there's more than one. So I could have just straight up and down. Have like this, that would be 2. But I could also, if these are perpendicular, go on the diagonal. So I would say this one actually has 1, 2, 3, 4 different lines of symmetry. And for the O, if we make it a circle, I would say go up and down, left and right, diagonal. But if it's a circle, you could keep drawing them in half. So when we think about that, we're thinking, well, how many lines are there then? Well, if we draw it like this, there are an infinite number of lines of symmetry. So an infinite number of lines of symmetry. All right, for number 5, for the letters X, H, and O, I want you to find the degree of rotation and plot the center of rotation. So when we draw this for X, let's draw it so that they're perpendicular. For H, draw it like this. And for O, again, it's a perfect circle. All right, so go ahead and think through this one on your own first, and then we'll check our answers together. All right, the center of rotation I'm going to do in blue. Center of rotation here would be right smack dab in the middle. So if I take this, and I have this X, and again I'm going to mark this corner here, just to know where I started. If I rotate this, and again if this was 90 degrees it'd be perfect, but it's not. So 90 degrees, it should map it onto itself if I drew this, right? So 90 degrees, 180 degrees, and now if we go past here, now we're just talking about past 180, and our degrees of rotation only go to 180, because if we go the opposite direction, we could cover that in the same degrees. So, so this would be 90 and 180. 90 degrees and 180 degrees. All right? With H, center of rotation again will be in the middle. And if I draw that, shoop, shoop. Again, mark this top little corner here so we know where we started. And if I rotate this, it's still not onto itself. So when I do 90 degrees, it doesn't get back to itself. But when I do 180, now we're back onto itself. And again, you could go past and do 360, but that would be the same thing as back at 0. So this one just has 180 degrees. And then finally with O, if we're talking about O being a circle, when you look at this, let's see if I have, use this tracing paper here. See how good I drew my circle. If I start rotating here, notice that it always is mapped onto itself. Always, always, always. I could rotate a half a degree. I could rotate 30 degrees. I could rotate 106 degrees. It'll always be mapped onto itself if it's a circle. So that is unique. So we have to think through, what would this be? Well, if X is the degree of rotation, to show that X could be anything between 0 and 180, excluding 0 degree, but including 180 degrees, we would write it like this. So that is an exception. A circle is very unique. All right, so that is your line symmetry. You can go ahead and get started on the homework.